Hello all, welcome to today's video. In today's video, we'll be looking at the algorithm find all numbers disappeared in an array. And I encourage us strongly to look at the last video, which was on the missing number. That algorithm will really, the knowledge we gathered there will help us in this particular algorithm. So I strongly encourage us to go back and watch that before we continue with this. Now, so this question says, the question here says, given an array's norms of n integers, where norms I is in the range 1n, we are to return an array of all integers in the range 1 to n that do not appear in the norm. So we are given an example here that 4, 3, 2. So when we check, 5 is missing, 6 is because 1, 2, 3 can find 4, 5 and 6 are not there, 7 and 8 are here. Also in this one, the length is 2, so that therefore it's supposed to be from 1 to 2, but 2 is missing from there. So we see the difference between this and that is, and the missing number algorithm is that for the missing number algorithm, we had that it only strictly one number that was missing. Here, multiple numbers can be missing and we have to return all of them as an array. And secondly is that that was from, I think, index 0 to, from number 0 to n. So this is from index from number 1 to n. Also, we are told that, okay, could you do it without extra space and in all of n runtime? So they want us to try and achieve that. So let's look at how we can come up with our solution for this. So I've taken the liberty to actually write down the example. So given we have something like this, so the first approach for me is to use a dictionary. So I have a store and I will go through the list and create a store from it. So I'll just have 4 is true, 3 is true, 2 is true, 7 is true, 7 is true, 8 also is true, 1 also is true, and 2 and 3 already exist in the dictionary, so that's fine. So having done this, the next point is to go through it, the list again. But this time around, we're checking, we go through from the index 1. So for example, we'll start from, we know that the length of this array is 8, so we know where to start from 1, 2, 3, 4, 5, 6, 7, up to 8. Those are the numbers that we are checking for because we know that since the length is 8 and we are told we are to start from 1, so we start checking from 1. We ask, is 1 in this dictionary? Yes. Is 2 in this dictionary? Yes. Is 3 in the dictionary? Yes. Is 4 in the dictionary? Yes. Is 5 in the dictionary? No. And so we add that to our output, to our array. Is 6 in the dictionary? No. So we add that to our array. Is 7 in the dictionary? Yes. Is 8 in the dictionary? Yes. And so what we'll be returning will be 5 and 6 as our response. That's as simple as it comes for the first approach that we have here. But if you look at this, it means that we have a dictionary which could possibly be up to O of n algorithm. An O of n time in terms of the time. And then, sorry, that's for the space, sorry, in terms of the space. And if you look at the time also, we go from 1 all the way to 8. So that's also an O of n algorithm. So, but they specifically told us that it's possible to achieve O of 1 algorithm. So, let me just create some space here. Okay, and create some space here so that we could use that. So, second approach we could use is that so we have our norms. Let me just put that down again. 4, 3, 2, 7, 8, 1, 2, and 3. Now, we could, using the approach we use for missing numbers, so let's have a box here just to make it easier for us. 2, 3, 5, 7. So this is index 0, 1, 2, 3, 4, 5, and index 7. And initially we have 4, 3, 2, 7, 8, 1, 2, and 3. Now, looking at this based on what we did in the missing algorithm, we start with 4 does, but now we know that this starts from 1. We will never have a number 0 within here in our values. It will always start from 1. So we'll just backtrack by one step. So we ask, this is number 4. We go to swap it with what is, when we remove 1 from 4, that is 3. So we go to swap it with what is index 3. So that will be from here to index 3, and then index 3 will swap back with it. So when we done with this, we should have something like this. Seven. So we should have 4. Okay, so it will have swapped. So that will be 7, 3, 2, 4, 8, 1, 2, 3. So we have that. We go to the next one. We are still here. 7, of course, definitely. 7 minus 1 is 6. So 0, 1, 2, 2, 3, 4, 5, 6, 7. So this is supposed to be in index 6. So we'll have that swap again. Then we swap it. So in the next loop, what will we have is something like 1, 2, 5. So index 0, 1, 2, 3, 4, 5, 7. And then here we have 7. We swap with 2. So 2 will be here, 3, 2, 4, 8, 1, and then 7 will have swapped. So we are still on at this index 0. We ask, 2 minus 1 is 1. So definitely this is not where it's supposed to be. So we come to this point, and so at this point 2 minus 1 is 1. So that means it's supposed to swap with this point. This and this will swap, and so what we will have is this. 1, 2, 3, 4, 5, 7. So 2 and 3 are swapping, so we have 3, 2, 2, 4, 8, 1, 7, and 3. So we continue. This is definitely no, so this is also still not where it's supposed to be. This is 3 minus 1 is 2, but it's in index 0, so it's supposed to swap with this, swap it again. Then we have this 1, 2, 3, 5, 7. So we'll have 3 swapping with 2 there. So this is 2, 2, and then we have 3 here. We have 4 here, 8, 1, 7, and 3. So that is at index 2. So the next thing we ask is 2 minus 1. Of course, that is not what it is. But when we come to 2, we see that it already exists there. So we can skip this and we go to the next point. So we are now at this point. So 2 minus 1 is 1, and it's in index 1, so it's fine. So we go to the next one. 3 and 3 minus 1 is 2, and is in index 2, so we know we are fine. We go to the next one. 4, and this is 4 minus 1, that's 3, and we're in index 3, so we know we are fine. We go to the next one. So currently we're on 8. You see 8 minus 1, 7. Definitely this is not index 7. This is 3, 4. This is index 4, 5, 7. So this is supposed to swap with this, so that what we have is something like this. 1, 2, 3, 4, 5, 6, and 7. So we have 2, 2, 3, 4. 8 will have swapped to this point, and 3 will be back here, and we have 1 and 7. So we come here again. So we are still at this point, and this is definitely not index 3. So 3 minus 1 is 2. So we come to index 2 and we find that 3 already exists there. So we know that it's already exists. So we go to the next, which is 1. 1 minus 1 is 0. This is not index 0. But when we come to index 0, that's not what is there. So it means that 1 swapping with 2 here. So we have this 1, 2, 3, 4, 5, 6, 7. So we have 2. Okay, sorry, we are swapping 1. So this is going to be 1, 2, 3, 4, 3, and we are swapping this with 2, 7, and 8 are here. So don't forget we are still at this point. So this is 2, and 2, the index 2, I mean number 2. So 2 minus 1 is 1. So we go to index 1, but we find that 2 already exists there. So we go forward. This is 7. 7 minus 1 is 6, and this is index 6. Go here. 8 minus 1 is index 7, and this is index 7, and that's the end. So what we now do at this point is, since what we have, we go start from the beginning, and we are checking. It should be sequential. So this is 1. Anyone that is missing, anyone that is not sequentially following means that's not in the correct index. So for example, I expect that 1 will be in index 0, 2 will be in index 1, 3 will be in index 2. So if we go through that, you see that 1 is index 0, yes, 2 is index 1, 3 is index 2, 4 is index 3, 5 is not in index 4. So we know that 5 is missing. 6 is not in index 5, so we know 6 is missing. 7 is in index 6, and 8 is in index 7. So our answer is 5 and 6. And here we did not really have to create another space, because in the question we have been told to assume that our response, our return array is not constituting any space. So in that case, it means that, and since we are using the array that we are given, it means that for us that we have been able to achieve an O of 1 space and an O of n time, which is what we are trying to achieve in the first place. So this is the algorithm we will be using to try and solve this with an O of 1 time complexity. Now, let's go back to this and let's see how we can solve the algorithm. So first off is that we remember that we are going from the first position, so all the way to the last position. So we're going from the first position, and we're going all the way, and at each point what we are doing is we are checking what is in that array at that index. So we want to check what's in the current index. No, let me use current value. I think that makes more sense. So that will be our norms I. So for example, at index 0, when we start, what is there is what we're asking. And so we want to, what we want to achieve is that, so if, for example, if what I am getting there is not equals to the index, so if I remove 1 from it and is not equals to what that index is, I know that I need to swap it. So for example, if I check for example, when we came here, we saw 4. When we remove 1 from 4, 3. Of course, that is not equals to our index, which is 0. So it means I know I need to swap it with what is in index 3. So basically, that's what we're trying to achieve there. So I could just create a variable. The next index will be current value minus 1, so we don't repeat that. So if the next index is not equals to where we currently are, we know that we want to swap. And we also do not swap if what is there is already what we are looking for. You know, so where the next index we are talking of. So we are also supposed to check if what is in the next index is not equals is not also equals to our current value, or we can just use I because that actually is what. So but let's just use current value, I think. So at this point, we know when we find a number that we can swap, so we can go ahead and make our swap. We want to check what we're trying to set is what is inside of our I, what is currently here. We want to swap it to what is in that next index, and then what is in the, and we want to put in the next index, we want to put what should be here. So we want to put our current value. That's basically what we want. So we're just making that swap. And when we're done with this, so if this is at this point, it makes a swap. If not, we want to go to the next. So basically, this will be while, I think, so that, or let me just put it if, and then we make this a while loop outside here, actually. So that's, so we can just make while I is less than constant length, and we just have the variable out here by I equals to 0. So starting from I. So at, but we know that if for any reason we have, so for example, if if the number I am is in the correct position, or if a duplicate already exists in that place, we want to go to the next index to check. So for example, we go back to our illustration here. When we, for example, 4 will swap because it doesn't exist. But when we got to this point here where we are checking for, yes, so we are checking for 2. When we're here, 2 already exists in 2 in index 1, 3 already exists in index 2, 4 already exists. So we know at each point when we find it already exists, we move to the next index. So basically that's what we're trying to do here. So if it's not in the correct index, we come and make the swap. But if it's in the correct index already, or the duplicate already exists there, then we want to go to the next index and continue our check. And so when we are done with our going through, we want to, so we need to, now we need, let's just create a list of integer, call it answer. Or we'll call it result, whichever we like. And so basically we'll just go from one, sorry, want to go from 1. We know it's supposed to go all the way to the length of that array, and want to, all we're just checking is if the norms, so because we know that so for example 1 will be in index 0, so I need to take off that 1 back. So if what is there, for example 1, so if I go into index 0, I'm expecting to find 1 there. If I go to index 2, I'm expecting to find 3 there. If I go to index 7, I'm expecting to find 8 there. So basically, if it is not what I find there, then I know that I just need to add it to my list. So answer.add, and I add what is there. So at the end of the day, we just return our answer and have that. So let's check. So there is, oh, sorry. So I already declared it as Evan. I put a list. The local parameter I cannot be claimed because name is used in. So, so I can't use I here. Yeah, so let's just go with J because I have declared I at the top level, so definitely I can use I. I is my default go-to alphabet when I'm working with algorithms, since I don't need to use very declarative names always. So let's see. Okay, okay. So it seems to be successful. Let's submit and see what we if it's optimal pass, and yes it is. So this is how we go about solving this algorithm efficiently without creating extra space, since our result is not seen as an extra space. We are just manipulating or using the input we are giving, and in place replacing the values. Uh, that's how we solve this algorithm. I hope you do it. Enjoy this video as I did making it. See you in the next video. Thank you.